Good evening, everyone, and welcome to another Quantum London webinar. Very excited today. We have a couple of great speakers introducing us to the world of software in the quantum world. And just for the few that are new to our community, just a couple of words on who we are. So Quantum London was born almost 2 years ago, yeah, almost there, and with the intention of creating a community linking the business people with the experts in the field of quantum technologies and quantum computing more specifically. So this is our mission, that's what we're trying to achieve, and what we do is we connect experts in the field with people who are curious about these new technologies, which is coming our way very fast, and also trying to build a community of people discussing these topics. So today, again, we have a couple of great speakers, and with me is Paolo Cuomo, the co-founder of Quantum London. And I will not take any more time. I know you're already keen to listen from our speakers. I will hand over to Simon McAdam and Matthias from Cambridge Quantum Computing, which will give us an overview of what they're doing in the space, as well as covering some real board use cases they've been working on recently. So Simon, Matthias, if you want to put your cameras on, I will let you do your own introductions.
Okay,
welcome.
So thank you. Thank you and hello everybody. Whilst Matthias shares the screen, I'll just say thank you to Paolo and Emmanuel for inviting us to speak today. Past sessions have been fantastic, so hopefully we can continue this high standard. So for the next 35-40 minutes or so, Matthias, my colleague, and myself will be helping you sort of make heads and tails of quantum computing for finance and in insurance. Next slide, please, Matthias. So I'm going to spend the first 10 minutes, no more than 12 minutes, giving you an introduction to quantum computing. So I appreciate many of you will be familiar with this, but just to make sure that we're all on the same page. And then I'll give a one-slide overview of Cambridge Quantum Computing and what we do here. And then I'll hand over to Matthias, who's going to do a lot of the heavy lifting today. He'll spend a good 30 minutes talking through different use cases in finance and insurance using quantum computers, with a focus on Monte Carlo simulations for using quantum computers. And then we'll keep the Q&A session until the end, if that's okay. And we'll have a good 10, maybe 50 minutes for discussions. So without further ado, Matthias, if you can switch to the next slide, please. Yeah, so sorry if I'm preaching to the converted here, but what is quantum computing? Well, as you may know, quantum computing is a fundamentally different approach to computing. Quantum computers aren't merely better classical computers. They are a completely paradigm-shifting technology. Quantum computers, of course, exploit quantum mechanical principles. You've probably heard of superposition, entanglement, even tunneling. These types of processes are very computationally expensive to simulate. Hence, we can use quantum computers and these principles to start to tackle particular problems, which we'll talk about in the next slide, to solve particular problems potentially dramatically faster than today's classical computers. So problems that might take longer than the age of the universe to solve, a quantum computer could do it in a few seconds. Or simulating a molecule, for example, you might need a classical computer larger than the size of the observable universe. Whereas if you could use a quantum computer that could fit inside this room. Anyway, next slide, please, Matthias. So what problems could a quantum computer solve? Well, in theory, a quantum computer could solve the easy classical problems, which is interesting but not much use because we would just use a classical computer, right? The more interesting problems are these problems that are difficult for a classical computer but are potentially easy for a quantum computer. And the two most famous examples are finding prime factors of large numbers, which underpins much of modern day cybersecurity. And the second one is using a quantum computer to simulate quantum mechanical systems. And there's many other different types of, sort of potential quantum algorithms that could be used to find a quantum speedup and hence quantum advantage. Quantum Algorithm Zoo in the bottom left-hand corner here is a great website to visit to see these. But much of these algorithms require large error-corrected fault-tolerant computers, which we don't have yet. We have noisy quantum computers with a handful of noisy quantum bits. So the question is, what use cases can we apply and use on today's noisy quantum computers? And this is what Matthias will be picking up in the next session with a focus on finance. But next slide, please, Matthias. So now that we have, we kind of know the problems that we could address, we need our quantum bits. So as you may know, quantum bits, much like regular bits, can be either a 0 or a 1, or heads or tails if you use the coin analogy. But unlike classical bits, quantum bits, qubits, can be some mixture of 0 or 1, like a flipping coin or a spinning coin. So we say qubits can be in a superposition over 0 or 1. So they could be 50% 0, 50% 1. They could be 90% 0, 10% 1. And it's not that we don't know what state they're in. We can manipulate these qubits using lasers and microwave pulses to control them. But eventually, when we measure them, they will collapse into 0 or 1 with a certain probability. So qubit number typically grabs the headlines. You can see the numbers sort of steadily increase, but qubit quality is equally important, if not more important. So IBM have developed this metric of quantum volume that takes into account not only the qubit number, the qubit quality, but also other variables like qubit conductivity and the compiler they're using, and many other variables. Next slide, please, Matthias. So now that we have our qubit, we need to build an actual device. So there's about 100 corporates and startups that are actively building quantum computers today. We call these computers NISQ devices, noisy intermediate scale quantum devices. They have perhaps less than 100 qubits, and these are noisy qubits. And these quantum computers can be split into different architectures. The most popular are these superconducting and ion trap architectures. Superconducting devices tend to be faster. They have faster quantum processing units, but are more error prone, whereas ion traps are the opposite. They are slower, but more accurate and have better connectivity. And then you have sort of other architectures, and there's many. Microsoft are famously pursuing these topological qubits that could function at room temperature. PsiQuantum are building these silicon photonic chips that they're trying to make a scalable process quantum rather than vice versa. And there's many more. So a question we typically get asked are, what's the best? And I guess part of the answer is, well, it depends what problem you're trying to solve, possibly. Whether it's a chemistry problem or an optimization problem, you might use different architectures. But in terms of which one's going to win the race, we don't know, nobody knows, and we at CQC remain hardware agnostic. We don't bet on any one horse, and indeed our software can function on potentially any backend, whether that is a hardware device or a simulator. Next slide, please, Matthias. So the hardware is advancing very quickly. You probably saw Google's quantum supremacy experiment last October, where they performed albeit a contrived experiment, but they did it in 2.5 minutes rather than 10,000 years for a supercomputer. And since then, especially in the last month or so, things have really started to speed up. So IBM announced a very impressive roadmap. They aim to build a 1,000-qubit quantum computer by 2023. They currently have a 65-qubit device. So that's on the superconducting side. And then on the ion trap side, Honeywell have an H1 10-qubit device that has a quantum volume of 128. And this is the highest quantum volume that is measured to date. And then IonQ is hot on their heels. They claim to have built a device that has a quantum volume of 4 million, which is comparable to 22 sort of effective qubits. And we look forward to seeing those results when they're released, hopefully in the future. So I guess the take-home message from this slide is things are advancing quickly and perhaps quicker than anyone had really anticipated. Next slide, please, Matthias. Yeah, so the hardware is getting better. We're getting more qubits, better quality qubits, but also the software is important as well. So we want to develop software that can utilize less qubits and less quality qubits. And the idea is that they will meet in the middle here and so we can demonstrate some quantum advantage. So when I say this, can we do something with a quantum computer that we cannot do efficiently with a classical computer? And that's what's really sort of, well, one of the reasons that the field is so exciting. And next slide, please, Matthias. So speaking of software, this is exactly what we do here at Cambridge Quantum Computing. So a very brief history. We were established back in 2014. We now have over 120 people. That includes 80 scientists, 40 plus PhDs, and we're spread across the globe in the UK, Europe, US, Japan, and Asia too. So what we do is we develop hardware agnostic enterprise quantum software for NISQ devices, and we work towards a scalable quantum advantage. So our software is split into two categories. One is our quantum software development platform called Ticket. This provides a native programming interface and tools for runtime management. It also enables us to be both language agnostic, so you can code your language, code your algorithm in different languages, and then target that to different backends, which includes various simulators and hardware, as you can see here. And then on top of Ticket, we built application-specific frameworks that leverage Ticket for chemistry, so looking at simulating molecules and solid-state material, quantum machine learning and optimization. We have a particular focus on finance, of course, but we also work on sort of manufacturing efficiencies, and then also quantum natural language processing, so using quantum computers to understand grammatical sentences. So something else that we do is that we also collaborate with end users and corporates to work towards quantum advantage for their particular use cases that we then sort of develop within these frameworks. So we've announced several, such as working with GSR Corporation and Nippon Steel. So with Nippon Steel, we're working on two projects, one around quantum chemistry, so simulating solid-state materials such as iron, and we've published a paper on this and have another one coming out soon. And we're also working on computational optimization, so trying to optimize one of their job scheduling processes on the factory floor. Another long-term collaboration we have is with Total. So we're looking at simulating carbon capture materials, specifically these metal-organic frameworks that are of high interest to the field. And we're also working with DHL. So Matthias actually presented this yesterday, a workshop with DHL showing how we could use a quantum computer to simulate the bin packing problem and knapsack problem for optimally packing boxes into vehicles. And then we also work with institutions as well, research institutions like CERN Open Lab, where we're doing work on Monte Carlo simulations using certified random numbers that we can generate from a quantum computer, and also looking at quantum generative adversarial networks. We have many other collaborations that we haven't announced yet, but hopefully will in the future. Okay, so I think that's my sort of 10, 12 minutes up. I hope that was useful, and please type your questions and I'll answer them at the end of the session. But yes, so thank you for listening, and I'll hand you over to the main event. Matthias, please take it away.
All right, thank you, Simon, and thanks from me as well for having us, Paolo and Emanuele. Very nice event. So let me now switch gears a little bit and walk you through a few use cases, or show you a few use cases that especially financial institutes and insurance companies are looking at currently for quantum computers. And then I'll give you a brief idea of how one would go about implementing a specific use case or a specific technique that is often used in these use cases, namely Monte Carlo. First, as you know, models in financial institutes and in insurance sectors have become much more complicated over the last few years and last decades. And this is partly also driven by regulators. So regulators continue to demand that institutes can evaluate accurately more complex instruments. So banks have to include more and more features of these instruments and evaluate the instruments accurately. And this has led to a large increase in compute-heavy tasks that banks and insurance companies are faced with. And they barely fit into overnight batches nowadays. So it's becoming harder to actually run all these simulations and calculations overnight when a local market is closed, for example. So naturally, people ask, could quantum computers help, or are there any benefits of using quantum computers for these kind of compute-heavy tasks in finance and insurance? And the answer is not that straightforward. And the reason is, what Simon also mentioned is, quantum computers are not just a magical tool that speed up every computation. Instead, you often have to look at the specific use case and also have to look at methods and maybe look at a problem that you have from a very different angle and try to see or develop new methods that could benefit from a quantum computer. So this is something that we see in our collaborations as well. It's not often that just a straightforward translation from a classical use case to a quantum use case, but really digging into the details, being creative, coming up with new ideas of how we could tackle a certain use case or a certain problem with approaches that are more suitable for quantum computers. And here first, let me give you a brief or very, very high-level view of how we see the current stage of quantum computing algorithms. So today's quantum computers are not yet ready to run any algorithm that you throw at it. Not any quantum algorithm will run and produce meaningful results. So if you have heard, for example, about the Shor algorithm, which would be able to factorize prime numbers into prime factors, which could in turn be used for breaking many of current cryptography schemes. This is a type of algorithm that you see on the left here, a type of pure quantum algorithm that needs a really big and fault-tolerant quantum computer, which we don't have today. The advantage of applying these kind of algorithms is that you can prove that there are certain speedups. So you can say you can prove that this factoring algorithm that I mentioned is exponentially faster than the best known classical algorithm for these problems. That is good. But on the downside, as I mentioned, these computers just don't exist yet. You need perfect control over gates. You need very low noise thresholds. And additionally, you have a problem of how to actually translate your classical data to be usable on your quantum computer. So instead, what the algorithms that we typically look at today is the algorithms that are shown on the right here. They're called hybrid algorithms. Sometimes they're also called variational algorithms. And here the idea is basically that you split your problem into parts that are usable or useful to implement on a quantum computer and parts that are well suited for classical computers. So basically you optimize the way how you use your quantum and classical resources. So basically the idea is that your classical computer does all the number crunching and your quantum computer does a certain sub-problem of your overall problem that is particularly good at. The advantage here is that you don't necessarily need perfect control over your gates, over your operations on your quantum computer. You can sometimes work around imperfections. You don't need necessarily high noise resilience. and you can tune your algorithms to a certain extent to the available noise thresholds. As I mentioned, you can combine classical and quantum resources in an optimal way, but that comes with a downside that these algorithms are typically a heuristic in nature. So you don't have a nice mathematical proof that this particular algorithm will really speed up your problem. It's just something that you need to try out and experiment with. So now let me start with a few of the use cases that we see in finance and insurance. And the main structure that I want to put onto these use cases is basically to structure them into these kind of three categories. So we have optimization problems, we have machine learning problems, and we have simulation problems. And then I've just listed a few of the use cases that we see that banks and other companies are looking at. And I will go into a little bit more details, some of them. Here, just a summary. So in optimization, what we see, for example, the canonical example for finance is this portfolio optimization problem. So here, the goal is basically to find a portfolio of assets. Could be stocks, could be some bonds, for example, or a mix of them, that minimize a certain risk measure. So this is the canonical example. You have a risk measure. You want to minimize your risk of your portfolio, but at the same time, you want to maximize, for example, your return that your portfolio would generate. And this is what is called a combinatorial optimization problem. And this is a type of problem that is well suited for quantum computers. There have been various papers that look into this with varying various methods, various techniques, various hardware backends. Similar problem, transaction settlement problem. Here, the goal is basically to settle transactions, to get some kind of a batch of many transactions, and you want to settle these in a kind of optimal way. And optimal could mean that you have certain limits that you need to observe. So you can only fulfill some of the transactions, etc. So this is again an optimization problem that central clearinghouses face, for example. Finding arbitrage, that means, for example, in the FX markets, you sometimes have possibility of trade different currency pairs. So, for example, you could trade in US versus GBP products. You could trade in GBP versus Japanese yen, for example. And then you could also trade directly in Japanese yen and US dollar. And so you have some kind of triangular relationship between the three pairs, and you could try to find arbitrage possibilities between these trading these pairs. Stress testing, another optimization problem. On the machine learning side, one of the cases here is fraud detection. So if you imagine a credit card company, you get an online stream of transactions coming in, and you have to decide in a very short amount of time, is this transaction fraudulent or not? And you have certain features of the transaction. For example, you could you have a currency, you have a POC, so some kind of terminal or an ATM that it originated from. And you have various features of the customer of the credit card that actually did this or originated this transaction. And based on this information, credit card companies use machine learning methods to quickly decide if this is a fraudulent transaction or not. And here, there are some ideas how to speed up this detection process or improve this detection process using quantum computers. They have also machine learning tasks in credit scoring. So here the idea is to decide if a certain loan can be granted or not based on certain features of the person that wants to enter this loan. And another big topic in machine learning is creating synthetic data. So you have some kind of, you could imagine, for example, a time series for some asset with holes in the history, and you want to basically fill this gap in your history of your time series, or you want to produce new data in the future. So here the idea is that you want to build a model of this time series and generate new returns or new prices that fit into optimally fit into your observed history. And this is used in for example, in calibrating models in risk. Also, you need full time series in risk. So this is a big topic, creating new data with machine learning. Simulation means, for example, in risk management, you want to simulate market movements. So you have, let's say, you want to simulate, let's say, scenarios of how the market could move within the next 1 or maybe up to 10 days. You have a certain idea or a certain model how the market could behave, and now you want to measure the risk of a portfolio based on this information of these scenarios of how the market could move. This is a risk management problem, and for that you need often need Monte Carlo simulations, and this is an example that we'll go into later on. Pricing financial instruments similarly can use Monte Carlo simulation to price, for example, options in finance. So options are financial products that only get executed when, for example, a certain underlying hits a barrier or hits a certain price at the end of the life of this instrument. Another idea that hasn't been explored much here is simulating partial differential equations. You can write down the evolution of certain instruments, financial instruments, as a partial differential equation, and then there are ideas out how to solve these partial differential equations more efficiently on a quantum computer. This is something that hasn't been explored much. There has been 1 or 2 papers on this, but there's an interesting new development. So now with that overview, let me now go into each of these blocks in a bit more detail and give you a bit of an idea of the timescales, roughly. So in optimization, we think that what I call discrete optimization problems are more of a near-term application for quantum computers. As we mentioned, I mean, today's quantum computers, the NISQ devices, noisy intermediate scale quantum devices, they are not fully fledged quantum computers yet, but we believe that the discrete optimization problems, so these are problems where you have discrete decisions problems. For example, you have a yes or no decision problem, where you want to optimize this kind of problem, this kind of discrete decision problem. These are the problems that might be suitable for these more near-term quantum computers. Combinatorial optimization, that is basically a subcategory of discrete optimization. You have a certain combination of in the portfolio optimization problem, for example. This would be a classical combinatorial optimization problem. You can you want to optimize a certain certain subset or a certain combination of assets in an optimal fashion. And optimal means, for example, finding the maximum returns given some constraints, like risk minimizing the risk, or other types of discrete problems like integer or mixed integer problems. What is perhaps less suited for today's quantum computers are large linear programs. So these typically are real valued optimization problems. They are also very compute intensive problems in real world use cases, but they might not be very suitable for near-term quantum computers, we think. Similarly, semi-definite programming problems, there are some ideas how to port them into more near-term frameworks, but this seems to be a bit further out than, let's say, the combinatorial optimization problems. At the bottom here, I've listed a few of the relevant publications or preprints by some of the leading banks in the world in the optimization field. So, for example, here in this recent paper by BBVA, a Spanish bank, they used methods from combinatorial optimization, or I think it was more of an integer problem. They use these quantum methods to optimize the problem of tracking indices. So if you think of, for example, you want to track the S&P 500 or let's say, I don't know, Euro Stoxx 50 index in an optimal way. And optimal means you don't want to trade all the, I don't know, S&P 500 has 500 instruments. So you don't want to trade all the 500 stocks, but you want to find a subgroup of these assets that still optimally replicates the original index, like S&P in this example. This again is a problem that falls into this category, combinatorial optimization or integer optimization, that might be very suitable for nearer term quantum computers. This one, similarly, it's a portfolio optimization problem done by the Bank of Australia. Here, this one is also interesting. Barclays did this transaction settlement problem that I already talked about. So here the idea is, as I mentioned, the clearinghouse needs to settle many transactions in a short amount of time, given some credit limit constraints. And again, and similarly, again, a portfolio optimization problem done by Standard Charters here. On the machine learning side, there are again a few machine learning problems that are perhaps more suitable for the near term. And we believe that what I wrote down here, what falls under the umbrella of generative models or energy-based models as well. These seem to be more near-term approaches of machine learning that are in a way quantum native. So these kind of generative models, you can imagine them as a probabilistic model of data. So you try to find a probabilistic probability distribution that models your data in an optimal way. And then you can do tasks like sample from this distribution efficiently, or maybe do some reasoning based on this probability distribution of how your data is structured, for example. And there's a fairly natural way to implement these kind of models on a quantum computer, because a quantum computer, in an abstract sense, is basically prepares your probability distribution. And you can sample from it, you can do inference on it. And in finance, perhaps very interestingly, these hidden Markov models, they fall under this generative model umbrella, and they have been used in finance quite extensively in the past to model time series. And this is an approach that hasn't been explored much in the literature. This is something that we are quite excited about and want to apply in the future as well. And there hasn't been much, as I mentioned, much in the literature. This paper by JP Morgan, basically it replaces, or it looks at a particular generative model called quantum GAN to improve one particular step in this option pricing problem that they look at. More long-term, perhaps, are, let's say, generic supervised learning methods, generic big data problems, because here the problem is often that of how to actually put all your huge amounts of data on a quantum computer. This is not easy not possible in a straightforward way often. So let's say generic supervised learning methods are often quite efficiently done with deep learning methods, and here it's a bit harder to see the quantum advantage in the near term. In the simulation space, here that basically boils down to Monte Carlo simulations and solving differential equations. On the Monte Carlo side, there's a famous quantum algorithm that speeds up Monte Carlo simulations. The original form of this algorithm is not suitable for NISQ devices, so this is why I put it here. And this is basically this original algorithm. It's more of a long-term goal. It needs a fault-tolerant quantum computer, but there have been recent developments on how to do Monte Carlo simulation also on NISQ devices. Basically, it gets rid of a certain step in this original algorithm and replaces it with classical post-processing done in an intelligent way. And this brings the Monte Carlo simulations a bit more towards the nearer term end of the time scale. And again, this JP Morgan paper implements basically a Monte Carlo simulation for pricing options. IBM has also published this paper on quantum risk analysis. This uses basically Monte Carlo simulation to calculate value at risk and expected shortfalls. So these are common risk measures used in banks to quantify risk. And there has been an initial paper on solving PDEs as well, PDEs that arise in finance by Lloyds. So now with this overview, let me now show you how we could think about implementing Monte Carlo as a use case, or give you some hints on how one could do it and what typical problems are that one would face. And the reason why I've chosen Monte Carlo is just because it's so widely applicable in finance and insurance. So here, this illustration is an abstract view of how Monte Carlo works. So Monte Carlo simulation, basically in the first step, you need some kind of model, some kind of distribution, for example, of how your underlying price, if you think of pricing some kind of option, for example, you need to have some kind of model of how the underlying of this option evolves. So you need some kind of idea of how this price evolves over time. This is the step 0. You need some kind of calibrated model. It could be, for example, a Gaussian distribution. So that means your returns would be distributed like a Gaussian distribution, basically. Then in the first step in your Monte Carlo simulation, you need to draw many samples from this distribution that you've calibrated here. Then in the second step, you need to apply some functions to this sample. If you stay in this option pricing, you need to apply some kind of function that produces a price basically of this option given this sample of your returns. And then in the last step, you need to estimate some kind of statistic. It could be a mean, could be a value at risk, for example. Just some kind of statistic based on many samples that we've drawn here. So let's say you draw 1 million samples here. You calculate some kind of complicated functions based on the sample, and then you just take a mean of this example. That could be one Monte Carlo simulation that you typically face. And as I mentioned at the beginning, these simulations, they typically run overnight in banks for whole portfolios or part of sub-portfolios, take a lot of time, and naturally here people want methods, or people have asked if quantum computers can help here, and yes, there are ways to do this, but it's not trivial to translate it. So if you look at the history of this problem and how people thought about it, how to do this on quantum computers, you will find a paper which introduces basically this amplitude estimation algorithm for this problem. So in principle, you could just go one-to-one. So if you look at these steps here now, I've basically just redrawn the same illustration, but chosen a different headline here. So this is basically the same steps that you go through in the quantum algorithm as in the classical case. You have step 1, draw many samples. Now you do this on a quantum computer. You draw many quantum samples. You apply a function. Again, you don't do it classically, but you apply a function on the quantum computer, and then again you estimate statistic using this amplitude estimation algorithm. So in principle, you could go and think that this is a one-to-one translation, but unfortunately, in practice, it doesn't work that easily. And I've listed some of the typical problems that you would encounter here. Number 1, this whole algorithm is not suitable. So you need to be more clever in the way you apply this amplitude estimation algorithm. And as I mentioned, there are improvements on this, and there are ways to circumvent this. But then another big problem is how you actually prepare, or how you actually draw samples here at the beginning. So how do you, if you have some kind of, for example, a multivariate Gaussian distribution, how do you actually teach the quantum computer or tell the quantum computer that it should produce samples of this classical distribution? And again, there are papers out there and ideas out there how to do this efficiently. And people have done this in various ways using, for example, machine learning methods or using efficient state preparation methods. But there are other ideas out there, and this is still actively explored in use cases in research, how to do this most efficiently for a given use case. Then you need to apply a function. And again, here, the problem is often that you cannot just run. I mean, in principle, yes, you could write down a quantum circuit or quantum program which calculates any classical function that you can come up with in principle. But what you will find in practice is that these circuits that you draw and these quantum programs to do it right here, they get very complicated very quickly, and so they're just not suitable to run on near-term devices anymore. So you often have to think very hard of how to improve this step, how to apply a given valuation function efficiently. And then, as I mentioned here, this last bit, this can be done by improving the amplitude estimation algorithm. So to summarize this, yes, Monte Carlo simulation might be suitable or is suitable for NISQ, but you have to really dig into your particular use case. And here, research and experimentation is really key to really do this successfully and show how to or go towards a quantum advantage in, let's say, in the near term. And now, at the end of my presentation, I just want to give you a little bit of a hint of how one actually programs or would go about programming these kind of algorithms or use cases on a quantum computer. And first of all, good news is you don't need to learn any new language. You can typically code in, let's say, Python, for example. And this has the additional advantage that not only the quantum part lives in Python, but of course you can also interface this with your classical classical post-processing, pre-processing, and the whole classical processing part of the algorithm, the overall algorithm. So yeah, you can continue coding your quantum computer in Python, and concretely, how is this done? So in quantum algorithms, or the way you think on implementing quantum algorithms on quantum computers is often in this type of diagram here. So often we think in very low terms. So this is a quantum circuit, specific quantum circuit. Typical diagram that you would think in if you want to develop quantum algorithms. This is kind of equivalent to very low-level classical programming, where you also have some kind of logic gates like NOT gates and AND gates, etc. So here, instead of on a quantum computer, you have different gates. You have these H gates. You have these kind of gates that somehow act on two qubits. So each line here is one of the qubits that Simon mentioned on a quantum computer. So here you have what is called a single qubit gate that only interacts on this qubit number 0 here. Here, this particular gate, it operates on 2 qubits. And then at the end, you want to measure this the state. And what this symbol does is just tells the algorithm that, okay, here I want to measure this qubit 1 and I want to write it into a classical bit, number 0 here. And similarly here, you measure the outcome of this first qubit and write the output into this classical bit here. So this is the kind of high-level circuit structure that people often think in when they think about quantum algorithms. And now how you would code this in a framework like Ticket. You would tell it, okay, I want a circuit with 2 qubits and 2 classical bits, and then apply this H gate on qubit 0, then apply this, what is called the C0 or CX gate on qubit 0 and 1, And then at the end, just measure all my qubits into these available classical bits. Now in the next step, you have this the circuit. Now you want to run it on a given hardware. So for example, in this code snippet here, I would want to run it on IBM quantum computer, but with Ticket, we can also easily change this to Honeywell, can change this line to INQ, etc., etc. So you can really easily retarget your circuit onto a different backend. What you need to do is basically compile your circuit that you specified here for this particular platform. And what Ticket does here in this step, it does all the heavy lifting for you. Basically, it optimizes your circuit, because oftentimes you have certain steps that are redundant in your circuit, or you have ways to rewrite bits of your circuit. Also, what Ticket also does is it maps your qubits that you specified here to the optimal qubits on the actual device. So for example, you want to use qubits that have very low errors, and Ticket does that for you, basically, dependent on the hardware backend that you provide here. Then finally, you send this to the device and basically retrieve the results. And results here mean, in this particular case, I want to do this whole experiment 10 times. So here it tells the device repeat this whole thing 10 times. And what we would get here is basically a list of 10 results of reading out these classical bits here. And what this circuit does concretely, it prepares a distribution. So this could be used in a Monte Carlo experiment as a first step, for example, to prepare a certain probability distribution here. It's a very simple one. It's not very useful, perhaps, in practice. But what you would get back in an optimal case from this particular circuit is basically a sequence of 0 zeros and 1 ones. And the particular distribution that you've prepared here would, these 0 zeros and 1 ones would come back 50-50, basically. So 50% approximately of the cases, you would get a 0 0 result. And in 50% of the cases, you would get a 1 1 result. And this is just to give you a hint of how you can imagine now that you could tweak this circuit, this quantum circuit here, and basically engineer probability distributions that are useful for your Monte Carlo experiment. And this is the first step in your experiment. And with this little example, let me open the floor and open the Q&A session. And thank you for listening. And now we are open for questions. Thank you.
Fantastic. Thank you, Simon. Thank you, Matthias. And we had a number of questions in the chat. And if there are any more, please feel free to include them. And then we will try to ask as much as possible. We have about 10 minutes left before we wrap up. There have been a number of questions around, machine learning. I think you have answered those in the meantime. If not, I will kindly ask the people to ask them again any specific points in the chat. But I will start otherwise with the $1 million question, which we get asked every time. So the question is, we heard it's accelerating, the algorithm is getting better, the software is getting better. But the question is, these algorithms are all predicated on reliable hardware and number of qubits. Realistically, how far off this is? And we know it's not an easy answer. It's not like it's at 6 months, 3 years. But if you will maybe give us the sense of what is the roadmap and what you think is going to happen. We discuss about pure quantum algorithms versus hybrid algorithms. How will be the dynamic? We'll see these two coexisting, so we will see a shift over time. If you could elaborate on that, on what you see the roadmap is going to be in the next future, that would be super appreciated.
Matthias, do you want to kick off with that? And then
I think Matthias had a problem with audio. Do you want to pick it up, Simon?
Yeah, sure. Okay, so yeah, that's a great question. So, there's a lot of papers out there that give. Sorry, I just turned my camera on. Yeah, so for machine learning, for example, I'm thinking of a paper from Nature that was published not too long ago. And for a particular QAOA problem, if you Google QAOA and max cut, they suggest you'll need, on the order of hundreds of qubits to achieve sort of a quantum speed up for this particular problem. So that's good. That's good news. I can't remember exactly what the error rates that they were looking at there. In terms of quantum chemistry, there's other good papers out there that, for example, simulating active sites of enzymes. I'm thinking of a paper from Matthias Treuer. They suggest that you need 100 sort of logical qubits to simulate this active site. But depending on the error rate of your machines, you add an overhead to this. So at today's error rates, you need about 15,000 physical qubits to encode one logical qubit. So we're looking at potentially 1.5 million qubits. But then as the error rates improve, the number of qubits you need drops quite dramatically. Yeah. So to sort of answer your question, there is the hardware element is incredibly important, of course, but then the software side where we're coming from as well, you can reduce the number of qubits that you require. So we published a paper fairly recently where we can sort of scale quantum algorithms up. So instead of needing 40 qubits to encode 40 variables, we would now need 20 qubits or 15 qubits to encode those variables. So things are progressing quickly on both the hardware and the software side. Anyway, I'll stop talking there. I don't know if Matthias wants to have a say.
I'm not sure Matthias answered the question, but I can give you the next one to him. So again, go on this point. So on the software side, so what is the trajectory there? You see hybrid algorithms being predominant in the short term and then moving to more pure quantum algorithms, or is they going to coexist at the same time and they will be used to solve different problems? I don't know if you want to speak this one up, Matthias, if you're there, or Simon, if you want to cover this one.
Yes. So right now, as you said, we have hybrid quantum classical algorithms. So we have a portion of the algorithm that runs on the quantum computer, and then we have sort of an optimization loop, if you like, that involves the classical computer, and then eventually the two will sort of converge on the optimal solution. So yeah, so right now I guess we're limited in the number of gates that we can run. So if you have like a quantum volume of 2 to the n qubits, you're looking at running a circuit, with their n qubits wide and maybe 3n gates deep. So that's how we have that sort of repetition loop, because you can't run your algorithms too long before the noise overwhelms the system. So yeah, and Matthias in that slide showed sort of the comparison between fully quantum algorithms. So if we can discover a fully quantum algorithm like Shor's algorithm, where you can take classical data as your input, form some quantum function, quantum algorithm, and then output some classical data, that's the dream. But they are few and far between from what we've seen. So I think we're going to be using sort of hybrid quantum classical algorithms for a while, and of course Matthias said this earlier on, that actually encoding your quantum your sort of classical data into your quantum computer is quite a big hurdle as well. That I know CQC and others are sort of starting to address this. But yeah, so I guess the short answer is yes. It would be great to use fully quantum algorithms on fault-tolerant quantum computers, but we're not quite there yet.
Fantastic, Paolo. Any good questions from the chat?
A couple of practical ones. So one was around the ticket. I don't know if you want to sort of touch briefly on sort of a commercial approach if people want to know more.
Yeah, so Ticket is free for non-commercial use. So if you want to try Ticket out, please do so, and let us know how you get on. I suggest your first port of call is our GitHub page, or we have a systems description paper that you can find on our website. I think it's called Ticket, a retargetable compiler, that's probably the best place to start. But PyTicket could be installed with a simple pip install, and yeah, let us know how you get on.
Excellent. And someone's just added, Frank, where can I okay, what can I currently use Ticket for in terms of work with NLP transformer models? I guess that's very specific. I don't know if you have a one-line answer to that.
I'd have to pass on NLP transformer models. I recommend contacting our Bob Cook, who's head of our NLP.
Okay, and there's another question. I can't find it exactly now, but someone was asking about sort of using the what IBM offer as a free solution to code. I guess again, as a sort of one-line overview answer, which people would you suggest sort of using Ticket versus maybe using one of the hardware providers' free solutions? How would you describe the difference?
Yeah, so if you're using Qiskit, which is a great resource, they've got tons of amazing material, IBM. So I suggest if you're using Qiskit, then you might as well download PyTicket Qiskit, because you get sort of the additional features of PyTicket. And it also means that once you code in Qiskit, you can then retarget your code to different backends, so you're not stuck with the IBM simulator. You could send it to another simulator. So I suggest whatever language or platform you're using, try integrating PyTicket if it's available for that particular front end.
Fantastic. And if people have been excited about this and the fact that we've been talking about sort of practical, real world problems relevant in the nearer term than what we discuss in some of our presentations, which is more about the longer term potential. What might they do to get their colleagues and managers excited beyond, of course, showing them a recording of this webinar?
Matthias, do you want to take that one?
Because I have.
Perfect. Well, maybe it's incredibly insightful what he's saying.
Sorry, I can pick that one up. So it's a fantastic question, how to get involved in quantum. I think start off by reading around quantum, seeing what the use cases are. Look at what other companies are doing. Maybe start attending sort of seminars, things like this is a good idea. Watching YouTube videos, and then if you're getting serious, you reach out to startups like yourselves, and start initiating some sort of dialogue, seeing if there is maybe a short-term POC that you could do, or if you're still looking to get some budget, maybe some sort of internal workshops to try and get management on board, to try and win some budgets is, I guess, it is my short answer.
Perfect. That's great. We like to try and finish on the hour, which is just a few moments away. Are there any final thoughts from yourselves before I wrap up?
No. Yeah, thank you everybody for attending and your questions. Please connect on LinkedIn. Please follow us on LinkedIn. You can reach your YouTube channel and follow us on Twitter, etc. And yeah, thank you to Paolo and Emmanuel for organizing this. This has been fantastic. And yeah.
Perfect. Well, thank you, Simon. Thank you, Matthias. We really appreciated that. It's, if we think just sort of a year ago, we were still at the point that many of us weren't quite sure if any of this was happening anytime soon. So, hearing some Matthias' examples were invaluable. So, yeah, thank you again to people listening. Thank you for joining us. There's a few more things planned before Christmas, which we'll share through the social media channels quite soon, and then an interesting program already building up for the start of the new year. So thank you very much and good evening.
Thanks from my side. Not sure if you can still hear me, but thank you.